Well, welcome back to the office again. Today we'll talk about numerical integration. And this is very much one part of the course dealing with the applied mathematics. We don't get into too many applications with physical systems, but we'll talk about applied mathematics. And you may think, I've had enough of math in my math classes. Well, this is different, really. This kind of applied mathematics is like a numerical recipe. And it's a numerical recipe that gives you power to do things. In particular, after this lecture, after you've studied this material and mastered it, you should be able to feel free to integrate most anything numerically, and it's easy. Okay? So this is a bit different from numerical integration from analytic integration, because analytically you have to be clever to do integrals. Numerically, they're a snap. They're easy to do, so you look forward to it. It's a different viewpoint. In addition, it'll help you understand the abstract concept behind integration. This is where it comes from. So after we study this material, integration is more meaningful, and it's a nice tool. So let's get on, and let's look at the next slide. Slide number 2. Slide number 2 talks about numerical integration, and it calls it quadrature. Now, quadrature is sort of a funny name. It maybe to some of you it sounds a bit of old English, and it is. Okay? If you remember quadrile graph paper, what's quadrile graph paper? Well, it's just a piece of paper with lines drawn on little squares. Well, the original way in high school, if you ever covered that, when people still use paper in high school, of figuring out an integral, doing an integral numerically, was to draw a graph, like we have here on the figure, and then count the little boxes that fit under the graph. Because what a definite integral is, an integral between limits a and b here, is just the area under the curve of the integrand, which we call f of x, as a function of x. So the area under the curve is the integral we want to evaluate. It's done by counting boxes, and therefore it's called quadrature, related to boxes. Okay. If we look at the next line here, on slide 2, we see that the standard numerical approach is to count boxes. I just said that. Well, that's right, but that's how we compute things. And the only difference in how we get good rules or bad rules for integration is how we treat the top of the boxes. The better job we do treating the top of the boxes, whether they're square, curved, or they exactly go through every point we can think of, the better job corresponds to the different rules. But essentially, they're all the same. So the real rule we use is the actual mathematical Riemann definition of an integral. Riemann, we deal with lots of mathematical geniuses, and these guys, typically guys in the past, managed to think out a lot of the work we're doing for other purposes. So here, this is the Riemann definition of a definite integral, and it says the definite integral from a to b of a function, the integrand, f of x, is just a sum. It's the sum of the function f evaluated at n points. That's n. Here it's 1, 2, 3, 4, 5 points between the limits a and b, times the width h of a box. So it's really just essentially the area of a box. The width times the height, f of x is the height. And if you take the limit when the boxes become very small, which means h goes to 0, and the number of boxes goes to infinity, then you get the exact value of the integral. Okay? So that's the Riemann definition of the integral. Numerically, we use essentially that definition as the algorithm, regardless of how fancy a name we give to the rule. The only difference is we never take the limit n go to infinity, because we have better things to do in our life than just wait around, and we take, rather than the height h, we try to change the height a little bit, and we call it the weight w, which is always going to be some fraction of the height, maybe more than a fraction, but related to the height. So this, equation 2 here, is our algorithm. All the rules follow this algorithm. And if you look at that algorithm, look at the function form, it's quite easy to implement on a computer. It's quite easy to program up. It just says, do a sum, so you can use a for loop, and you sum over the function f, evaluated at n, capital N is the number of points, and it's always the number of points that we're using in the approximation. We evaluate the function at those points, and we multiply each point by a weight. And now we have to talk about how you determine those weights. But that's all there is to it. And we'll give 3 or 4 methods about determining weights, and then we'll try it out on the computer. But that's all you do, just as simple a rule as that. So let's look now at slide 3. Slide 3 warns you ahead of time that we're going to have 4 different rules we'll use for quadrature, for numerical integration. We'll talk in this little gathering about 3 of those rules. And the 4th rule is a Monte Carlo method. So that's a method involving chance, random numbers, and that's different from all the others, but it's actually the best way of doing these multi-dimensional integrals. If you were trying to integrate over, I don't know, 27 electrons in some atom, then you wouldn't want to use our rules, you'd want to use a Monte Carlo integration. If you were trying to do a 1- or 2-dimensional integration, then you'd use the rules we talk about today. So for big problems, Monte Carlo is best, but we'll see about that. Okay. The rules we'll talk about today then are just 3 rules, and they all correspond to using different approximations for the integrand within each interval. One of them will use a straight line, another will use a parabola, and the third will actually fit a polynomial over the whole region of the function. Okay? So, the first rule, the simplest rule, is the trapezoid rule. And that's the one where we just approximate the function by a straight line. So go ahead and look. Look at this picture. What does it say? Well, it says I'm not a very good artist, probably, but it probably also says that, okay, so here we have a function, f of x, with some S-shaped curve lying on its belly, or its back, and we have a bunch of trapezoids we've drawn under it. What's a trapezoid? Well, it's just a regular figure with straight lines. So here the bottoms are always flat. The top here has an angle. It's like a little triangle added to a rectangle. We have a bunch of trapezoids. That's the approximation. We'll calculate the area for each trapezoid, add them together, and that'll be our approximation for the integral. Simple as that. Okay, so what's the area of a trapezoid? Well, you could work it out. The hard way is to say, let's add together the area of a little triangle to the area of a rectangle. Or you could be clever. Let's look at this last trapezoid and see. The one labeled trapezoid 4. And you could see here, it has a height on the left side, which is just the value of the function at point x sub I. And for shorthand, we'll call that f sub I, the value of the integrand. On the right-hand side, we have the height is just the value of the integrand at point x to the I plus 1, so that's called f to the I plus 1. So the average height of this trapezoid is just 1/2, because it's an average, times the sum of the heights of the ends. So the area of this trapezoid is just 1/2 the height, f1 plus fij, times the width, h. So if we look at equation 1, that's the rule. It says if you were to do the integral of some function over just one interval, I to I plus 1, that's the labels we use for x, the answer would be 1/2 the height at one point plus 1/2 the height at the end point. And you could see this is just like what I warned you about. This is just the kind of integration rule. We have the function evaluated 2 places, and we have a weight. In this case, weight that's proportional to the width, h, 1/2 h. Fine. So that's, if all you had to do was evaluate one trapezoid, that would be the rule. If we look now at equation 2, we say, okay, if we have a whole interval going from A to B, which could be large numbers, we have to make many, many small steps. And since this is a very simple rule, we're keeping all the step sizes the same. It's what's known as a uniform step size rule. And we have to add the result, which is just the area of each of these trapezoids together. Well, here's, for one trapezoid, we just take 1/2 of the height at one end plus 1/2 of the height at the other times the width. Well, so when we add the trapezoids together, let's start here on the left. We get a 1/2 h for the first interval at the beginning. At the end of the first half interval, we get 1/2 h. But then for the second interval, we get another 1/2 h for the same height, because that corresponds to the second interval beginning. And then the end of the second interval, we get another 1/2 h, but that gets repeated again. So when we do the whole integration from a to b, as we see here at the bottom of equation 2, we see that we get a weight of h over 2 at the beginning, and we get a weight of h over 2 at the end, because they're only counted once. But all of the intervals in the middle have a height, f sub I, which is counted twice with h over 2, so we get h for each of those. So we get a weight of 1/2 at the ends and a weight of 1 in the middles. That's the trapezoid rule. We'll have to try it, and you'll do that in the lab. So now let's move on and look at the next slide, slide number 4. So slide number 4 talks about the next rule, a next simple uniform spaced rule. It's called Simpson's rule. It should be called the parabola rule, but Simpson got there first, I guess, and he named it, so it stuck. Okay, so here, rather than drawing straight lines between the tops of each interval, we actually draw a parabola, which is smooth and rounded, and probably has to fit the function a bit better than a straight line, unless the function happens to be a straight line, in which case parabola will fit it just as well, because it'll be a straight line. Okay? So, look at a parabola. The general form of a parabola is some function ax squared plus bx plus c. Okay? So that's the form of a parabola. So we have 3 constants, a, b, and c here. And so if we wanted to fit a parabola to just the function in one interval, say just this first interval here, we'd have the value of the function at 2 endpoints. That's not enough information. And you can't determine 3 unknown parameters with just 2 data points. We need 3 data points. No real problem. All you have to do is use 2 intervals. Because if you have 2 intervals, you have the function 1, 2, 3 places. That's all you need. And that's what you have to remember. To use the Simpson rule, where you fit parabolas, each parabola is fit to 2 intervals. So that, you have to have an even number of intervals in order for the rule to work. And if you look at just one interval, here's one interval, say in the middle, one interval has 2 endpoints. So you have to have, there's always one more endpoint than there is an interval. So for the number of intervals must be even, then the number of points we use in the integration must be odd. And that's a standard error beginners make, maybe even professionals make. They'll use the rule, Simpson rule, for a wrong number of points, for an even number of points, and they'll make a little mistake. Okay, so you can't do that. Okay, so well, how do we do this now? How do we add together all these intervals? Well, we have to do 2 things. First, we have to figure out the area of one parabola, under one parabola, and then we have to add them all together. It's just a bunch of algebra. It's not very hard, but it's a bunch of messy algebra, so we show that on the next slide. So let's go to slide 5. Look through slide 5. Not a bad looking slide. Okay, what do we have? So we have our graph here again. We still have that for the single parabola. We want to fit a, b, and c to 3 values of the function. And in the textbook, I go through how to do that. I actually work it out because people never believed me that it was simple. It's just a bunch of algebra. And what you get is, as expected, the answer has to depend on the value of the function at the 3 points, and 2 ends in the middle, and some fraction of h. Well, it turns out the weight is h over 3 for the first point. It's symmetrical. It's h over 3 for the end point. And the middle point has this funny weight, 4h over 3. And that's just the way the numbers work out. So that's the area under one parabola going through points f sub I minus 1, f sub I, and f sub I plus 1. 3 values of the function. So we fit a parabola to the function in that interval. That's the parabola, that's the area. So what if we add together now all the parabolas making up the interval from A to B? Well, it's just like the trapezoid rule, only it's a little more complicated because we add 2 intervals at a time to another 2 intervals. And we get h over 3, 4h, h over 3, but we get the end point of one interval begins the first point of the next interval. So the h over 3 always gets repeated twice, except at the ends, a and b, of the total integration region, when it's not repeated. So we get h over 3 in equation 2 here, h over 3 at the end points, fine. Then in the middle, we get the 4h over 3. That's the, for the first interval here, that would be the midpoint. That does not get repeated, so that stays. But the end point, which was h over 3, becomes 2h over 3. It seems like a lot of words. Don't worry about it. Here's the rule again. As always, we have an odd number of points. We're just summing over this should be the function f at x in equation 3. Should be the function at f of x sub I with different weights, w sub I. And the weights are just h over 3 times 1, 4, 2, 4. That's what's written down. That's what you have to, to use. Okay. So then repeat here, equation 3, that should be the function at x sub I. Okay. So now let's look at slide 6. So in slide 6, we give you a review. These are the two rules we've looked at. The trapezoid rule evaluates the function from a to b as just the sum of the function at all the intermediate points times a height h over 2 at the beginning, h over 2 at the end, and h in the middle. The Simpson rule, which has to be better, still keeps equally spaced points, but it evaluates it with a weight h over 3 at both ends, and then there's alternating 4h over 3, 2h, 4h, etc. So this is a better rule, but it's more complicated. You do the same number of function evaluations, but the weights have to alternate. So when you program it up, you have to be able to tell even or odd apart. So these are the two basic rules. As simple-minded as they may be, they're used all the time. Even when you get sophisticated schemes, you often have to start off with the trapezoid rule or the Simpson rule. And then you move on. So now let's go on and look at a more complicated rule. Okay, so let's look now at slide number 7. So on slide 7 here, we have the third integration rule, Gaussian quadrature. And it's marked with a star or an asterisk. And some of you may be saying, aha, asterisk means it's optional, therefore I'll just forget what this guy's saying up there. Well, sometimes that might be true, although usually we'll use his O for that. The star here means that this is the golden rule. This is the standard that working scientists use all the time for integration. It's just such a good rule, it's hard to believe it works so well. Okay? So as we see on equation 1 here, it still follows the whole basic idea. The integration from between some interval a to b of a function is still just the sum of the values of the function in that interval times some weights. And all Gauss has done is he figured out a better way of doing the weights and a cleverer way of choosing the points. So here's maybe a way of looking at it. Gauss was given the challenge. If given n points for an integration rule, what's the best I can do? Okay? If I wanted to evaluate the function just n times, what polynomial could I fit to this function, what degree polynomial, and have it the best integration rule possible? Well, you'd say, you already told me when we spoke about Simpson's rule that I needed 3 interval points, 3 values of the function to determine 3 constants. So the obvious answer would be n points will determine an nth degree polynomial. Well, for you and I, that might be a good answer, or n minus 1 degree to be more precise. But Gauss was a genius. He was a mathematical genius. And, these geniuses can do things, they see solutions to problems that we may not. And what Gauss said is, no, I'm twice as good as you guys. I can fit a 2n minus 1 degree polynomial given n evaluations. And you let me choose the points. And never in your wildest dreams will you be able to guess where the points come out to be. But Gauss did this, okay? And it would take an hour or so to prove this, and we can't do that. Probably I couldn't do it anyway unless I studied harder than I'm willing to, but Gauss solved this problem. So let's talk both about what the solution is and how you use the solution. Okay? So here again, we have now a function we want to evaluate, but the values of x will not necessarily be uniformly spaced. In fact, they won't be. None will occur at the endpoints, and they'll be symmetric around the middle. They're called Gaussian quadrature points. And what Gauss discovered here on equation 2 is that the points occur at the zeros of the Legendre polynomials. So he did a simpler problem. He said, let's just integrate the function from -1 to +1. Okay? And then we'll scale one way or another, answer to A or B, whatever you want. And then it's exactly the zeros of the Legendre polynomials. In other words, it's the values, x correspond to the values where the polynomial is equal to 0. Why that? Well, that's where you have to go through the derivation to figure it out. And what are the weights? The weights are a little less obvious yet. The weights are related to this function here, which is 1 over the Legendre polynomial derivative evaluated at the zeros of the polynomial. That's not very hard to do numerically, but it's not something you'd guess. Okay? So the usual rule is you just evaluate these Gaussian quadrature points and weights either with a mathematical function, which we give you, or look it up in a table someplace. You don't figure it out yourself each time because it's a little bit tricky, a little bit sophisticated to get them accurately enough. And then, since the values of y here are used deliberately because they only occur between -1 and +1, which is the range for the Legendre polynomials. And if you need them for any other range x, which is what we usually use for our integration variable, you just scale it. So here we have x is equal to b plus a, which is the average midpoint, plus some scale value of y. So this will scale uniformly the x's to the y's, and the weights just scale appropriately. So that's all there is to it. Okay? So how do you actually do this on the computer? Well, let's look now at slide 8. Slide 8 is a program. So we give you on the CD that comes with the book the program integration-gauss.java. And here's a simplified version of it. Leaves off the output statements. And what it does is it just has a main program and it says, okay, let's try Gauss integration. So it calls a method, GaussInt, and it calls it for a different number of points, from 3 up to 11 points. So that's the number of integration points. That's the first variable here. And an integration region, A and B, A corresponds to 0, B corresponds to 1, and it does integration. So all you have to do is call this, and it does it. Fine. The function being evaluated is math.exp, which is just the exponential function of -x. Nothing you'd ever use the computer to evaluate because you can do that analytically. But it gives us a chance to check the method, which is what we want you to do. We'll talk about that. And the actual integration, Gauss integration, is done down here, the bottom. But you can see most of what it is just a summation, just a for loop, and it's just summing dummy variable quadrature, which is the answer, the function f evaluated at the Gauss points, times the weight corresponding to each point. Where the square bracket indicates an array, these are just subscripts. How does it get the points x sub I? It just calls a method, which we give to you. We won't show you here because we'd hate to have you shriek in horror. So we just call the method Gauss, the number of points, anything you want, a code, that's to scale it the simple way, from A to B, that's minimum max, and then it returns two arrays, x and w. X are the points, w's are the weights. So you probably haven't followed everything I've said, but you should feel relieved. We're giving you how to use Gauss quadrature. You can take this with you. It's been developed by years of hard-working graduate students, their thesis research, and it's worked very well, and we hope you enjoy it as well, too. Okay. So slide 9 comes the real interesting part. The part of the exercise here which you just don't find in a numerical algebra book, but something you have to do as computational science. So take a look at slide 9. In slide 9, we talk about integration errors. And recall, we talk about errors other places in the textbook, other places in the lectures here. Now we actually get to apply them to a real interesting case. But we won't go through many of the details here, both because it's very algebraic, it's hard to go through the algebra, and I'm getting tired of doing this. I want to get on and try it out. So we talk about error. And error is defined to be the relative error. And that means the numeric error numeric value of a function minus the exact value divided by the exact. So for our test cases here, we know the exact value. That's why we're integrating an exponential or something like that. So we can compare that to the numerical. And recall the trick we learned. If we take the logarithm of this error, log to base 10, then we get a negative number, and that number will be approximately the number of significant figures in the answer. So in other words, if our numeric and exact answer differed in the 8th place, the difference would be like 1 times 10 to the minus 8th times the exact answer, but then we divide by the exact answer, so the logarithm turns out to be 10 to the minus 8th. So we take the absolute value of that logarithm, we get the number of decimal places. So here, in this graph, we show a plot. It's a semi-log plot. The error, absolute value of the error, notice that it's a logarithmic scale on the ordinate, and n, the number of integration points, is not on, it's also a log scale, 10, 100. So that's also a log scale, so it's a log-log plot. Okay, and what do we have? We show here that, the rules seem to work. What does that mean, the rules are working? Well, the rules work in that the error decreases for all 3 of these rules as we increase the number of points. If that was not happening, we wouldn't have an algorithm. Because, you know, algorithm is supposed to be a recipe for doing something which gets better as you use more points. Okay, so that's called approximation error, as you recall, and we're saying that the approximation error decreases, the purely mathematical error, as we use more points, as well it should. In the textbook, we do a bunch of the analysis, and we say that the total error has 2 parts usually. There's the approximation error, which comes purely from the mathematics, and then there's the round-off error, or truncation error. And that arises because we only are using a finite number of digits to store the numbers. And at some point, you get noise due to that, and the noise tends to accumulate. And what you have to notice here is, this garbage at the bottom looks like noise. That's the round-off error. And what we said when we studied errors is round-off error as a model increases like the square root of n. And what you can see here is, well, I don't know if that's the square root of n, but it certainly does not get smaller, the junk, the noise at the bottom. If it increases slowly, that's what we said, and the square root of n is not bad. Okay? So the algorithmic error falls off rapidly. It's a straight line on a log-log plot. What does that mean? That means it falls off like some power of n, some inverse power of n. Okay? Whereas the other error, the round-off error, grows, and that's the whole business. Okay? So if we look in the text, we do the analysis, and it's not very hard. It's nothing more than Taylor expansion of a function. We find that for the trapezoid rule, that's the rule where we have straight lines on the top, the error goes like the second derivative of the function, of the integrand, times something else, and that something else is of the order of something that goes like the integrand size, the interval size, divided by n squared. So the error for the trapezoid rule falls off like 1 over n squared, where n is the number of points. And if we do the same analysis, which is not hard to do, try it sometime, for the Simpson rule, the error falls off like 1 over n to the 4th, which is faster. And if we look back at our graph here, and you're going to have to produce a graph like this for your laboratory work, we see, sure, the trapezoid rule falls off like maybe like 1 over n squared. The Simpson rule has a slope which is roughly twice as large. And that's what this is saying. Okay, so, and the Gaussian quadrature, which we have not done the error analysis, falls off very rapidly. But it's sort of like, also like some power, but even yet some higher power. And it's a higher power rule. Here it falls off so very rapidly that we can't even see much of what the slope is. It just works too well. And then immediately it becomes noisy. Okay? So that's the interesting part. Let me review that immediately because there's 2 points you have to remember. One, the algorithmic error must decrease with n. If it doesn't, it wouldn't be a good algorithm. But sooner or later you face the real world, which is that if you do enough steps, if n gets larger and larger, adding enough numbers together, the error you made due to round off, due to truncation, must come in, and that comes in, and it wins the battle in the long run. So where do you quit? What's the best number of points you should use? Well, here's how you determine it experimentally. You want the best number of points to be the number when you start getting this round-off error coming in. Typically, you only know that for some model like this where you know the exact answer. But you can do the analysis, and you can say, what happens if we set the algorithmic error, which we know algebraically, equal to the model we use, the square root of n times machine precision, as that's our model for the round-off error. If we set the two errors together, then we get, and we can solve the equation for a value of n, which is the best value of n to use. And that's what we do on equation 2 here. So we have that, we've set the two together, and we actually predict, based on 1 over n squared, 1 over n to the fourth for the two rules, we predict that the trapezoid rule gets its best precision for about 631 points, and the Simpson rule gets its best precision for about 36 points. If we look at the graph, we see trapezoid rule is good. That's 1, 2, 3, about 400, 500 points, pretty close to our approximation. Simpson rule is good here, 10, 20, maybe around 30, very close. And then what error is obtained? This is a single precision calculation just to make things go quickly. The trapezoid rule gets roughly 6 decimal places. The Simpson rule gets 7 decimal places. What's the lesson here? Well, yes, the Simpson rule is more accurate, but not for the reason you'd think. The Simpson rule is more accurate not because it's a better rule in that it's more precise. It's more accurate because it does as many calculations. Because it's faster, doesn't have to have as many steps, there's less chance for round-off to accumulate. So in 36 steps, it gets roughly 10 times better an answer than the trapezoid rule using 600 steps. Okay? So the smaller round-off error is what's very important. So I think you deserve a break. Okay? So this was a lot of hard work, and now we're going to see that this stuff really works. Okay? And you won't learn it until you try it out in the lab. So now, let's go out to the lab. Oh, we're in the lab. Okay, so let's get down to work. What do we want you to do? Well, we want you to actually try out these integration rules and, get your hands dirty. I hate toys, So, how do we do this? Let's look now at slide number 11. Okay. What we want you to do is conduct your own empirical error analysis. We want you to estimate the error, make a graph like this. Now we did this graph with the exponential function. You can integrate any other function whose answer you know, but keep it something without wiggles to start with. We'll talk about that. Okay? So use the trapezoid rule, use Simpson rule, use Gaussian quadrature, learn how to use that program we gave you, get it running, to calculate some integral. So here, when we tried with e to the minus x, I'd suggest x squared times e to the minus x also. Calculate the function from 0 to 1. The answer should be 1 minus e to the minus 1. Calculate the relative error, numeric minus exact over exact. Take the absolute value of that and take the logarithm of the absolute value. Has to be the absolute value because the logarithm of a negative number does not make the computer happy. And you take the absolute value of the answer because we just want a positive number, and plot it up, either that or use log paper, and plot the number of points, the logarithm of the number of points versus the error, or the error on a vertical scale. And what you should find is a straight line to start with, Gaussian, Simpson, trapezoid. Once you've found that straight line, we want you to deduce. You can do it by hand if you want. You can use the computer. Once you have the graph, figure out the slope. And you should get the slope to agree roughly, or see how well it does agree with the numbers we predicted in the text. You should get the trapezoid rule. It has about half the slope as the Simpson rule in magnitude. Simpson rule falls off more quickly. Gaussian falls off even more quickly. Estimate roughly what the fall off should be. You should get a log plot, which is a straight line. Okay. Then, once you know these methods work, go ahead to slide 12 here. Try some interesting cases. Okay. The first case is shown by this white graph. It's a graph of just a sine wave which begins and ends at some point. And what's the integral of this over some region, let's say the whole region, any one part? Okay? So if you want to say, okay, let's first do the interval from interval, but do the whole interval. Then let's just do one peak or half a peak. What answer do you get? Well, you have to be careful here because the total integral is the total area under the curve, and the areas add algebraically. So there's negative area when the curve goes below the horizontal axis, and there's positive area otherwise. So the exact answer here is 0. And one of the rules of thumb for computation is you can never calculate zeros accurately. Why is that? Well, for one thing, if you try to calculate the relative error, you divide by 0, you always get infinity. And even if you use the exact answer, you divide by a very small number, you'll also tend to get a very large number. So integrals that give you 0 or nearly 0 as an answer are hard to calculate. You should get a small number on some scale, but figuring out what scale that is the problem. So here, for example, when we ask you also to calculate f1, f1 is some integral from 0 to 2 pi of sine of 100x. Well, 100x is an oscillatory function, and as x gets larger, it oscillates even more, but the answer should be a small number. Is it 0? We'll let you figure out if it's 0 or not. Play with it. See how well you can calculate that. And the third formula we want you to calculate is sine to the power x of 100x dx. That's also going to be a challenging problem, and I'll give you a hint, but I won't give you the answer. The hint is, just because you have a computer, even if it's the world's most powerful computer, and we've showed you how these integration rules are powerful and how they're simple to use, doesn't mean they can be applied every place. Mathematics still holds. And there's some aspects of this function, x being a variable that varies from 0 to 2 pi, there's some aspects of that function which will be hard to calculate. So we'll leave that for you. See what the computer gives you. So that's all for now, and I think you should have happy computing and integrate to your heart's content. Bye-bye.